Welcome to the Deep Dive, where we transform complex information into clear, compelling insights, really cutting straight to the most important nuggets of knowledge.
That's the plan.
Today, we're embarking on a fascinating journey, really getting into the world of infrared spectroscopy, or IR.
That's right. Our mission for this deep dive is, well, to equip you with the understanding of how this powerful analytical tool actually functions.
Yeah.
And what it uniquely reveals about a molecule's structure.
Okay.
And critically, how you can actually look at an IR spectrum and interpret it, to pinpoint those crucial functional groups.
And we're drawing this all from Chapter 18 of Organic Chemistry, I for Dummies.
A second D. Exactly.
Yeah.
Distilling it down to the absolute essentials for you.
Okay, let's unpack this then. When many of us visualize chemical bonds, I think we tend to picture them as fixed, like rigid little sticks.
Yeah.
Right? Especially from those neat molecular diagrams you see.
The standard ball and stick models.
Yeah. But the source makes it wonderfully clear that's, well, far from the truth. Bonds are incredibly dynamic.
Yeah, absolutely.
Constantly stretching, bending, flexing, rotating even. It describes them as behaving kind of like springs that are in constant motion.
That's a great analogy, actually.
So when we talk about a bond having a specific length, that's really just an average then. These tiny molecular springs are always vibrating.
Always. It's inherent.
So what does this constant invisible motion mean for how molecules interact with light? How does that connect?
Well, what's truly fascinating is how that spring-like dynamic behavior directly connects to the fundamental principles of IR spectroscopy.
Cool.
Just like a physical spring, each chemical bond vibrates at a very specific intrinsic frequency. It's not random at all.
Right.
This frequency is precisely determined by two main factors, and it applies a concept similar to Hooke's law from physics, the one describing how springs vibrate.
Ah, okay. Hooke's law. So it's the very physical properties of the atoms and the bond itself that dictate its unique vibrational rhythm.
Precisely. The first factor is the mass of the atoms involved in the bond. Lighter atoms attached to a bond will always vibrate at a higher frequency than heavier ones. Think of it conceptually. A light spring just oscillates faster than a heavy one, doesn't it?
Yeah, that makes intuitive sense.
The source gives a really great example to illustrate this. If you compare a hydrogen bond, HH, to a hydrogen deuterium bond, HHD.
Where deuterium is the heavier hydrogen isotope.
Exactly. The HH bond will vibrate at a noticeably higher frequency. It's simply because lighter things oscillate faster. It's a principle that holds true from, playground swings right down to molecular bonds.
Okay, lighter things bounce faster. Got it. What's the second factor, then, that influences this vibrational signature?
The second key factor is bond strength.
Strength, right.
Stronger bonds, just like stronger springs, they require more force to stretch, right? So they'll vibrate at higher frequencies.
Okay.
This means triple bonds, which are the strongest common type, vibrate at higher frequencies than double bonds.
Makes sense.
And for the same reason, double bonds vibrate at higher frequencies than single bonds. It's a direct relationship. Stronger bond, higher frequency of vibration. Pretty straightforward.
So we've established that bonds are these tiny, constantly vibrating springs.
Hmm.
The critical question then becomes, how do we see that invisible dance? What does it take for a molecule's vibration to actually register on our instruments?
Well, we can't directly see them in the visual sense, of course. But here's the magic, the connection to light. If light with that exact same frequency as the bond's natural vibration hits the molecule...
The resonant frequency.
Exactly, the resonant frequency. Something special happens. The light energy is absorbed by the bond. And an IR spectrometer is designed to measure this absorption. It works basically by sending one beam of infrared light through your sample, and a second identical beam, the reference beam, through an empty cell or solvent.
Right, a baseline.
Precisely. The machine then compares the intensity of light coming out of your sample with the reference beam, frequency by frequency.
And if less light comes through the sample?
If less light comes out of the sample at a certain frequency, it means that specific frequency of light was absorbed. Simple as that.
Okay.
This absorption directly indicates that a bond in the molecule is vibrating at that exact rate. And, as the name suggests, the specific frequencies required to excite these bond vibrations happen to fall precisely in the infrared region of the electromagnetic spectrum.
Hence, infrared spectroscopy.
You got it.
Now, as I was reading this, a question kept nagging at me. It's one thing for a bond to absorb light. Okay, I get that. But what makes some of those absorptions just tiny little blips on the graph and others these massive, undeniable peaks?
Yeah.
What dictates the strength or intensity of that signal?
That's a really crucial point, and it's absolutely key to interpreting spectra effectively. The intensity of an absorption depends almost entirely on the change in the bond's dipole moment during the vibration.
Dipole moment. Okay, remind me.
Remember, a dipole moment is essentially a measure of the separation of positive and negative charges within a bond, how unevenly the electrons are shared.
Right, like in water, H2O.
Perfect example. So, bonds that undergo a large change in their dipole moment when they stretch or vibrate will have very intense absorptions in the IR spectrum. It's like they create a bigger wave in the electrical field for the IR light to interact with.
So if there's a big shift in electron density back and forth during the vibration, the absorption will be stronger.
Exactly. Consider common bonds like OH, NH, and CH. Oxygen is highly electronegative, right? It pulls electrons very strongly.
Very strongly.
So, stretching an OH bond creates a very large dynamic change in that bond's dipole moment as the atoms move apart and back together.
Okay.
This results in a very intense, often broad, unmistakable absorption in the IR spectrum. You can't miss it.
Right.
Now, nitrogen is less electronegative than oxygen, so an NH bond stretch produces a smaller dipole moment change. This leads to weaker absorptions compared to OH.
Still visible, but less intense.
Yeah, generally yes. And CH bonds, well, carbon and hydrogen have very similar electronegativities. So stretching a CH bond causes only a minimal change in dipole moment.
Ah.
Which means CH bonds typically have the weakest absorptions among these three common types. This hierarchy of intensity, OH strong, NH medium, CH relatively weak, is a really powerful visual clue when you're looking at a spectrum.
And conversely then, what if a bond vibration produces absolutely no change in its dipole moment? Is it just invisible to the IR spectrometer?
That's exactly right. Invisible.
A powerful paradox in IR, isn't it?
Yeah.
Sometimes no signal is actually the most telling signal.
Absolutely. If a bond motion produces no net change in its dipole moment, it simply won't absorb IR light at that frequency at all.
Right.
These are critically important to recognize, and they're called IR-inactive vibrations. They just won't show up in an IR spectrum, period.
And when does that usually happen?
This often happens in very symmetrical molecules, where stretching a particular bond doesn't actually alter the overall charge distribution. A classic example the source gives is the Cl-Cl bond in chlorine gas. It's perfectly symmetrical. Stretching it doesn't create or change a dipole moment.
Makes sense.
Another common one is the carbon-carbon triple bond in something like dimethyl acetylene, where you have methyl groups on either side. It's symmetrical, so stretching that triple bond doesn't change the dipole. It's IR-inactive.
So if you're expecting a peak for a bond, it must be there, like a CEC double bond in ethene, and it's missing.
It screams symmetry. It tells you the molecule must be symmetrical around that bond. That can be a critical piece of the puzzle, especially for highly symmetrical molecules that simply don't dance in a way IR can detect.
Okay, fascinating. So we have this machine. It zaps molecules with IR light, measures what gets absorbed. What does the output actually look like? How do we read this thing, this IR spectrum? It seems to plot transmittance against these rather unusual units of CL.
Yeah, the units can throw people off at first. By convention, an IR spectrum plots light transmittance on the y-axis. That's the percentage of light that passes through the sample.
Okay, %T.
Right. And on the x-axis, it plots the frequency of light, but measured in wave numbers, which is CMOA. Wave number is just 1 over the wavelength in centimeters, so it's proportional to frequency and energy. It tells us how many waves fit into a centimeter.
Okay, higher wave number means higher frequency, higher energy.
Exactly. Now, this can be a bit counterintuitive because a low transmittance value on the y-axis actually means high absorption.
Ah, right. Less light got through, so more was absorbed.
Precisely. So what we typically refer to as a peak when talking about spectra is actually a dip downwards on the IR graph, representing where a lot of light was absorbed by a specific bond vibration.
Got it. Peaks point down.
Peaks point down. And the most useful aspect of IR, the reason it's so powerful, is that similar types of bonds, like all CO double bonds or all OH single bonds, show up in very specific and predictable regions of the spectrum, pretty much regardless of the rest of the molecule structure.
Okay, that predictability is key. Now, the source mentions something called the fingerprint region. What's that about? And why is it often advised, especially for beginners, to largely ignore it? Is it really that useless for initial analysis?
Ah, the fingerprint region. Good question. The region roughly between 500 centimeter and 1500 centimeter is indeed known as the fingerprint region.
Why fingerprint?
Because every unique molecule has an absolutely unique, complex pattern of absorptions in this area. It's like a molecular fingerprint incredibly specific to that one compound.
Wow.
However, for beginners or even for initial analysis, this region is usually just, well, a complex mess. Lots of overlapping peaks from various single bond stretches and bends. It's really challenging to interpret in detail unless you know exactly what you're looking for or have a reference.
So for finding functional groups, look elsewhere first.
Generally, yes. For initial analysis and identifying the major functional groups, it's often advised to focus outside this region, say above 1500 centenary, because the signals there tend to be much cleaner, more isolated, and more directly related to specific groups like CO or OH.
But don't dismiss it entirely.
Definitely not. The fingerprint region is incredibly useful later on for confirming the identity of an unknown compound. If your unknown sample's fingerprint region perfectly matches the spectrum of a known reference compound,
They're almost certainly the same molecule.
exactly, it's powerful confirmation. So it's great for proving identity, but maybe not the best place to start for figuring out the structure from scratch.
All right, this is where the rubber meets the road then. We've got our graph, peaks point down. We understand roughly what's happening with vibrations and dipoles. But how do we become molecular detectives?
Haha.
How do we use these seemingly abstract squiggles to actually uncover the hidden identities, the functional groups, within an unknown compound? This seems like the primary modern use for IR, right? Quick functional group identification.
This is the primary modern use of IR spectroscopy, absolutely. It provides a quick, powerful initial insight into what kinds of building blocks are present.
So how do we start? Where do we look first on the spectrum?
Okay, the standard approach is to first use the CH absorptions, which typically appear in the region from about 2800 centiroot to 3000 centiroot. Use these as a kind of baseline or frame of reference.
Why CH?
Because almost every organic compound you'll encounter has CH bonds, so these signals are nearly always present. And even though individual CH stretches are relatively weak in terms of dipole change,
Right, we cover that.
a typical organic molecule has so many CH bonds that their overall absorption usually appears quite intense, as a jumble of peaks in that 2800-3000 range.
Okay, so find the CH forest first.
Find the CH forest exactly. Once you've oriented yourself with those, you then look for distinctive signals in two key areas. First, to the left of the CH absorptions, meaning higher frequencies, above 3000 centimore.
Okay.
And second, to the right of the CH absorptions, meaning lower frequencies, usually between about 1600 and 2800 centimore, just before you hit that really dense fingerprint region.
Got it. Left of CH, right of CH, but above the fingerprint. Let's start with those higher frequency absorptions to the left of the CH absorptions, above 3000 centimore. What are the big players we should be looking for there, and what do they typically look like?
Okay, this region contains some of the easiest and most distinctive peaks to spot. They really stand out.
Good.
First up, alcohols, OH. These are usually incredibly easy to identify. They appear as a big and fat or very broad absorption, typically somewhere between 3,400 and 3,700 in centimore.
Broad is the key word.
Absolutely. Their very broadness isn't just a visual quirk, it's a direct spectroscopic fingerprint of hydrogen bonding between alcohol molecules.
Ah, the intermolecular forces.
Exactly. This fundamental interaction shapes water, DNA, proteins, countless biological systems. So IR doesn't just identify alcohols, it visually reveals the unseen hydrogen bonding forces holding molecules together. It's quite profound, really.
Oh, okay, so look for the big, broad peak above 3000. What else?
Next, amines, NH. These are also important. Primary amines, that's RNH2, meaning they have two hydrogens attached to the nitrogen, are quite distinctive.
Oh, so?
They show two smaller, sharper peaks, usually around 3,300 to 3,350 centimore. The source colorfully describes this double peak as looking like a cow-udder.
Chuckles. Okay, a cow-udder. Got it.
Secondary amines, RNH, with only one hydrogen on the nitrogen, have only a single absorption in the same general region.
Can you confuse that single peak with an alcohol?
Sometimes, yes, especially if the alcohol peak isn't super broad, but amines are usually thinner and sharper than OH peaks, and alcohol peaks are typically much broader and often more intense. Practice really helps in telling the difference here.
Okay, so OH broad, NH sharper, maybe doubled. What else is up there?
If you have a terminal alkane, that means a carbon-carbon triple bond at the very end of a chain with a hydrogen directly attached to it, CSEH,
Right.
you'll see a strong, distinct, and usually quite sharp alkenyl CH stretch right around 3,300 secamera. This is a very specific indicator for terminal alkenes.
Sharp peak at 3300 means terminal alkene. good to know.
And finally, a really crucial distinction. Any CH stretches that appear slightly above 3,000 Salmonera, say 3010 to 300-150 Centiero, are a very good indication of an alkene or an aromatic ring.
Wait, I thought CH was below 3,000.
Normal alkene CH bonds bonded to sp3 hybridized carbons are below 3,000, but CH bonds attached to CO2 hybridized carbons, the carbons involved in double bonds, alkenes or aromatic rings, vibrate at a slightly higher frequency. So if you see CH signals above that 3,000 centimeter dividing line, it tells you immediately you have CH bonds on an sp2 carbon. That means you almost certainly have double bonds or an aromatic ring present. It's a key diagnostic feature.
Okay, that's super useful. Above 3,000 for alkene aromatic CH, below for alkene CH. Got it.
Exactly.
All right, let's shift our gaze now. We've looked above 3,000. What about the other side of the CH baseline, that region between fingerprint and CH, say roughly 1,600 to 2,800 centimeter? What major players do we find there, and what do their spectroscopic signatures reveal?
Right, this is another really important region. This is where many common and often intensely absorbing functional groups reside, and their signals are often quite powerful and distinct.
Like what?
The biggest one, arguably, is the carbonyl group, CO.
The double bond to oxygen, found everywhere.
Absolutely. Aldehydes, ketones, esters, carboxylic acids, amides, they all have it. And in the IR spectrum, carbonyls are typically big and tall, meaning a very intense, usually quite sharp and thin absorption.
Like a finger pointing down.
Exactly like a finger pointing down, usually centered somewhere around 1,700 centimetero, maybe 1,680 to 1,750, depending on the exact type. If you see a strong, sharp peak around 1,700, your first thought should absolutely be carbonyl.
Okay, strong peak near 1,700 is likely CO. Are there variations?
Oh yes, subtle shifts tell you more. For example, conjugated carbonyls, that means a CO group right next to a C-C double bond or an aromatic ring, tend to appear at slightly lower frequencies, often below 1,700 centimoa, maybe 1,680. This is due to resonance, electron delocalization, weakening the CO bond slightly.
Okay, conjugation lowers the frequency.
Right. And ester carbonyls, OCOR, tend to be at slightly higher frequencies, typically between 1,735 and 1,750 centimoa.
Higher for esters.
Generally. And carboxylic acids, OCOH, are really unique and easy to spot.
How so?
Because they have both a carbonyl stretch, often a bit broad itself, around 1710 centimo, and that incredibly broad OH absorption we talked about earlier from the OH group. But for acids, this OH stretch is often so broad due to strong hydrogen bonding dimerization that it can even overlap and merge into the CH stretch region below 3,000 centimo. It's this huge, broad trough from maybe 3,400 down to 2,400, plus the carbonyl peak. Very distinctive.
Wow, okay. So the combined CO and superbroad OH screams carboxylic acid.
Unmistakably.
What else is in this 1,600, 2,800 region besides carbonyls?
Well, you can often see the alkene sequel C double bond stretch itself. These usually show up as weak to medium intensity peaks, somewhere between 1,640 and 1,680 centimon.
Not as strong as carbonyls.
No, generally weaker because the dipole moment change isn't as large. But remember, you can also look for that alkene CCH stretch above 3,000 centimor to help confirm the presence of an alkene. It's a good class reference.
Okay, CC around 1,650, weaker.
Got it. Then you have alkynes, C, the carbon triple bond stretch itself. These typically produce medium intensity absorptions in a higher range, between 2,100 and 2,250 centimor. Quite distinct.
2,100, 2,250 for the triple bond.
Yep. And right near there, you also find nitriles, CN, the carbon-nitrogen triple bond. These are also usually medium intensity and typically appear between 2,200 and 250 centimor, so they overlap somewhat with alkynes. Context usually helps tell them apart.
Okay, C and CM both around 2,200.
That's the zone. And finally, aromatics. We mentioned their CH stretches are above 3,000 cMR, but the aromatic ring itself, the C-C bonds within the ring, often produce a series of small bumps or weak absorptions in the 1,650 to 2,000 cMR region, often called overtone or combination bands.
Bumps.
Yeah, they're usually weak and look like little bumps on the baseline in that area. The exact number and pattern of these bumps can sometimes give clues about how the ring is substituted, mono, ditri, substituted, etc. But that's a more advanced interpretation skill.
Okay, so multiple weak bumps between 1,650 and 2,000 might suggest an aromatic ring.
It's another piece of supporting evidence, yes.
Wow. What an incredible deep dive into IR spectroscopy. I mean, from understanding how bond vibrations act like tiny springs, constantly in motion.
Yeah, it's a dynamic picture.
To navigating the spectrum, knowing peaks point down, using CH as a landmark, and then pinpointing functional groups like finding specific landmarks on a map, OH broad, CO a sharp finger.
Mm.
It's clear this is such a powerful tool for any chemist.
It really is.
It seems to offer a unique shortcut to understanding molecular structure, helping you identify those key building blocks quickly without needing to perform, I don't know, a dozen different chemical tests like in the old days.
Absolutely. That's its main strength today. Now, while NMR spectroscopy, nuclear magnetic resonance, has certainly become the go-to technique for really detailed atom-by-atom structural analysis in modern organic chemistry.
Right. NMR gives you the full picture eventually.
It does, allowing chemists to truly see every atom's environment. But IR remains absolutely invaluable for its speed and its ability to give you that immediate critical information about the presence or absence of specific functional groups. Are there alcohols? Is there a carbonyl? Is it an acid?
You get that answer in minutes.
Exactly. It really demonstrates how different analytical techniques complement each other beautifully in the pursuit of chemical knowledge. They each offer a unique lens, a unique perspective through which to view the unseen world of molecules.
And for you, our listener, hopefully this knowledge means you're now equipped to understand a bit more about how scientists see this unseen world just by interpreting these good vibrations, you could say, that molecular bonds are constantly making. Perhaps this deep dive encourages you to look for the invisible forces at play, the hidden rhythms and motions in the world around you, maybe even beyond chemistry.
Indeed. It's all vibrating.
Chuckles.
It is. Thank you so much for joining us on this deep dive into IR spectroscopy. We really appreciate you being a part of our deep dive community.
It was a pleasure.
We'll catch you on the next one.